define the artificial neuron. So what is the artificial neuron? It's basically the perceptron that you had with one tiny difference. The tiny difference here is that you don't necessarily need to put a step function here, right? So you can put any function here, and as long as that function is nonlinear, you're just doing fine, okay? So if we want to formally define an artificial neuron, this is an artificial neuron. So it's going to have a bunch of inputs. So in general, n different inputs can go inside the neuron. And at the output, you're going to have a single scalar right now, okay? We're going to make it like a network of neurons, and then you're going to have as much outputs as you want. But one single neuron right now, what it does, it's going to get a bunch of inputs, and then you're going to have one single output. And how does it work? It essentially has n different weights, so weight 1 to weight n. Every single one going to get multiplied with the corresponding input. They add up to the bias, go inside the activation function, and at the output, you're going to have your scalar output. Now, one thing here that I'm going to do from now on is that, first of all, when I want to show a neuron, I'm going to put the circle and write down this function f inside it, okay? So that f is essentially the activation function, right? The last thing that you have in this architecture. And most of the times, I would drop all of the weights here, right? So I'm not going to show the weights. I probably drop the bias as well. But you should always think any circle, any node with a function in it is essentially taking any input, multiplying them with their corresponding weights, adding up potentially a bias, and then passing it through that function, right? Everybody's cool, right? So this is what we are going to call artificial neurons. So this is the perceptron. As I said, the only difference here is that you have this function f, which is now we're considering it to be general, right? So this is how you can write down the relation between the input and output. So you have your weight vector is getting linearly multiplied with x, the inner product here, and then you're going to add up the bias. So you get your vector x at the output. You have a single scalar, right? So that z value before activation is a linear transform of your x, right? And then that z value, that linear transform, is activated by function f. So w is the vector of the weights, b is the bias, and f, as I told you, this is what we call it activation function, right? Now, activation function, theoretically, you can put any function here, right? So for perceptron, we had activation function to be the step function, right? You might decide to put it a linear function, right? If you put it a linear function, then you're going to reduce to the simple linear model, the one which we use to just solve the projectile problem, right? And you can think of any nonlinear function, and some of you who have some experience, you know that neither linear nor a step function are good choices, right? And you're going to see gradually why they are not good choices, okay? But you can potentially put any function there. So that function could be anything. It could be the linear function. This means that whatever comes inside that function, it's going to get directly out. So y then is going to be exactly equivalent to the argument, which is the basic linear model, right? So this is a much more, say, general form as compared to what we had before, right? And it's just somehow capturing all those models. Cool. So this is one single neuron. And one key factor here is that as we saw inside the universal approximation theorem, the key factor was that we get, for example, the line, right? And then we start to classify. We say here is 1, here is 0, right? And then again, we draw another line. We say here is 1, here is 0. So the key factor here is that you need always, if you want to have represent a very complicated function, then you always need this function f, the activation function, to be something nonlinear. It doesn't need to be like a super weird function, but it should not be linear. It should not be the straight line, right? So what are the choices? The most famous choice is ReLU function. This is a nonlinear function, but it looks very close to a linear function, right? So what is a ReLU function? Whenever the input is positive, it's going to pass. Whenever it's negative, it's going to be 0, right? So it's going to be the max of x and 0. So whatever comes in gonna pass if it's positive. If not, it's gonna get 0, right? It's gonna get replaced by 0. So this is a nonlinear function because when I give any x, I don't see the exact x at the output, right? So that's enough amount of nonlinearity that you might need, okay? But there are also some other choices. For instance, the sigmoid function. This is also one famous choice. And this choice is, again, nonlinear, as you can see. I mean, obviously nonlinear. And the expression is in this form, so you can write it down as 1 over 1 plus e to power minus x. Now, one question. If x goes to minus infinity, what's going to happen? It's going to be 0, right? So when x goes to minus infinity, this is exponential of plus infinity, right? And the denominator is very large, so essentially that guy is 0, right? What's going to happen when x goes to plus infinity? It's going to be 1, because the exponential term is going to disappear. It's going to be 1 over 1. It's going to be 1. So you see, at minus infinity, it's 0. It's going to just go up till 1, and then it's going to saturate at 1. And what is the value at 0 if I put x equal by 0? It's going to be half. It's going to exactly cross the vertical axis on half, right? So this point that is crossing, this is exactly half. So it's a kind of symmetric shape above and below, right? Everybody's cool, right? OK. Now, yeah, go. Why we need nonlinear activation? Yeah, so I guess either in the assignment or in one of the questions that I give you later for self-practice, you can simply see that once I make the layered neural network, you're going to see it more obviously. But the key point is that when you have multiple layers of a neural network, if you don't have nonlinear activation, then you essentially have, say, one matrix of weights, again, matrix of weights, and so on, right? And then from very beginning to the very end, you can represent everything, again, with one matrix of weights, right? So it doesn't matter how deep you make it. If you don't have nonlinear activation, all of it going to be seen as a giant linear layer, right? And then it's not going to learn any nonlinear function, right? The only way that you can make it learning a nonlinear function is that you have nonlinearity at the activation. And you don't really need to make it super complicated. As I said, like even ReLU is enough. So actually a very long literature. I put you one paper about universal approximation theorem. But if you read that paper or if you check it and you go to the references, the citations, the people who have cited that, like they're pretty much for every single activation function that you can think of, there is universal approximation theory. Like people come over and say, OK, let's say the nonlinearity is ReLU. Then again, they can show this is enough to just show any function. Sigmoid, it is enough to show any function, and so on. Okay. No worries. Yes?
So if something is in nature is linear, if you put non-linear function for its output still be linear?
You mean that I want to learn a linear function using a nonlinear model?
Because sometimes we don't know the fact that it's linear or non-linear. We just put it into the model. But maybe the fact that it's supposed to be a linear.
Yes, but I guess you can eventually, I should see what problem exactly you have in mind. But if, for example, you think of classification, you can always represent that simple linear separable problem. Also, you can do it by a nonlinear model. Because, I mean, the only thing is that, like, say that this is like extremely, this is linear, and you have a very deep neural network, right? If one of the neurons has right weights, everybody else is 0, then eventually you're going to end up having one linear classifier, right? So it's no problem that you get from the complicated to simple. The problem is that you use a simple model to just represent a complicated function, right? And to don't get into that position, you need to always have nonlinearity. No. Questions? No question? OK, cool. So yeah, this is Another typical choice of activation function, the sigmoid function, you could have tan h. So it pretty much looks like the sigmoid function, but it just starts from, it's going to be -1 to 1, right? Right. So if you set x to go to -infinity, then you eventually, you need to factor it out, and then you're going to be -1. If you just put it +infinity, then again you factor out, and you're going to get 1, right? So again, it's the same rays, and then you're going to see that exactly at this point, you're going to be 0, right? And you could have other functions. For example, this is what we call a soft ReLU function. So it's essentially the ReLU function that we had was 0 and then linearly going up. But you don't want the edge, right? You don't want the function to be non-differentiable. You're going to see why we don't want non-differentiable functions. And then this is what we call it soft ReLU. Again, if you look at it here, if x is significantly large, what's going to happen? I can simply ignore this 1, right? So when x is very large, e to power x is significantly larger than 1. So now this log of 1 plus e to power x, you can roughly say this is log of e to power x, right? Which is x itself, right? So when x is very large, it's going to look like a linear function, right? Again, when x is very small, so x goes to -infinity, then you can say it's pretty much 0, right? And then log of 1 is 0, right? So it's going to be 0, and then it's going to look like a linear function in extreme cases, but somewhere between around 0, it's going to look smooth, right? This is what we call it soft ReLU. And then sometimes it's going to be a useful choice when you don't want, you're very obsessed with no non-differentiable point in your activation. So now, these are typical choices. You could have other choices as well. Typically, for many applications that you can think of, ReLU is the safe choice. You can go ahead with that, unless we're going to get to the sequence models, and some sequence models need more sophisticated activations. So now, what is an artificial neural network? Then artificial neural network is essentially a network, a graph, a directed graph, where you have lots of nodes, and all of these nodes are the artificial neurons, right? So you say that I have this directed graph, that I have a bunch of inputs. Say I have 2 different inputs, x1, x2. This is the whole input. This is my image, for example, my audio, whatever the signal, the data is that I want to give to my model, right? And at the output, I have one particular output, for instance. Say I have here just one output. And then I can connect these inputs to the output through one graph, right? So I can put a bunch of nodes in between, and then I can connect the input to those nodes. Those nodes, again, can get connected to other nodes, and so on until I arrive to the output, right? So this guy, as long as every yellow node here is an artificial neuron, then this is what we call it artificial neural network, okay? And then from now on, I'm not going to call it artificial neural network. Neural network is enough, right? Because we do know that these are not real neurons, right? Okay, so this is what you call a neural network, nothing complicated. Basically, the perceptron, if you just play with the activation and then you put them together, then you have one neural network, right? Now, for this neural network, there are a bunch of things that we can define. For instance, we can define the depth. What is the depth? The depth is the longest path you're going to take from one input to the output. The longest path, not the shortest path. Okay? So let's look at this guy here. So this is the network that we had. If I want to get from input, say I want to get from x1, my path could be as short as x1 directly to y, right? So my path could be as short as 1, right? But this is not the longest path, right? So the longest path is going to be x1 going to f3, going to f2, and then to f4. Or, for instance, x1 to f3 to f1, and then f4, right? So you again take longer path, right? So if you want to think about the depth, it's like you put the information at the input, and each time that information is passed from one node to another is one time interval, right? How long you should wait till you are sure all the information has passed, right? This is somehow like that, right? This is what we call it depth. Okay, now here, what is depth? 3, right? So I'm going to get 1, 2, 3, and now I'm at the output, right? So I'm going to have 3. The depth is 3, okay? So the depth here is 3, right? Yes?
Is this defined per input, or is defined for the whole network based on how long is the input?
There's no concrete definition, but usually whole network.
Okay.
Like if, for example, x2 has a longer path, then you're going to say that is the depth, right? But typically we always use layered networks, so we're not going to get into that situation. Yeah. So everybody's cool about the depth, right? Now, what is a deep neural network? The deep neural network is whose depth is very large. And what is that large? More than? 2, yes, exactly. So when you say you have a deep neural network, you simply mean that the depth is more than 2. Not 2 itself, is 3 or more, right? So there's no more, say, definition into it. It just, if you have more than depth 2, then you're going to have a deep neural network, okay? So, for instance, what we had here, this is a deep neural network, even though it doesn't look like one. But this is a deep neural network by definition, because it has depth 3, and 3 is more than 2, right? So it's a deep neural network. Everybody's cool? Yes?
In the previous slide, you said like it needs to be the graph needs to be
Directed,
directed.
yes. Well, yeah, because there's always one, there are outputs coming out of the nodes and inputs going inside the nodes, right?
That means like it can be cyclic, so I can go from F4, for example, to F1 again.
Yes, you can. You can have cyclic network, yes. We don't do it in the first 2 parts, but when we get later, like into sequence models, you actually get cycle. So you get from time. Sorry?
There's some advantage to that.
Yes, if you want to just process a sequence, then you need cycle. Because like you get your first, say, sample in the sequence, and then you process it, you compute something out of it, right? And you keep it. Next time, you're going to give it back to the input, right? And it's going to get processed with the next part of the signal, right? And then you're going to carry memory with its process. So this is why we do it later. But right now, we're not doing it, right? But you can eventually have the cycle, right? So everybody's cool? Okay. So now, here, this is, as I said, a deep neural network because the depth is 3. And now, typically, not typically, always, in practice, we have a layered neural network, right? So we don't have that weird neural network that I showed you. We always have neurons put into layers, right? And what is a layer? Eventually, the layer is, we define a layer to be a set of neurons who are all in the same distance from the input, right? So every neuron in the first layer here is in distance 1. Every guy in the second one is in distance 2, and so on, right? Everybody's clear? Yeah? Now, crazy things could happen. We're going to do things like this in the course, right? Like, for example, I get X1, and I just directly connect it to F, right? So this is what we call a skip connection. We'll later do it when the network gets super deep. Or we could get back in. I mean, this is not a typical thing, but in some weird architecture, you could have that one as well. But right now, you just don't think about them, okay? Just let's start simple. Think of feed-forward network. Like everything goes in, and then it just passes layer by layer towards the end, okay? Everybody's cool? So here, this is like, 2 layers in between, and then you have the output layer, okay? And when we have these layered architectures, then typically we call each layer, we give each layer a kind of name. So we have 3 different kinds of layers. The first one is the layer which contains all the inputs. I mean, theoretically, it's not a layer of neurons, right? So you don't have any neuron here. X1 to Xn, all of them are your input, right? But you assume that they are somehow sorted in one layer, and you call it the input layer, right? So the input layer is where you put your input, your data in, right? Your data sample just sits there, right? And then it starts to get processed through the neural network, right? Now, when it's gonna just process layer by layer. At the very, very end, you are going to do a bunch of computations, and that is going to give you the output, right? The very last layer, right? That last layer, which is returning the output to you, this is what we call it output layer, right? Everybody's clear? So that last layer is eventually containing neurons, artificial neurons, and they are the ones, the last neurons in this network, which is doing the computation for you, right? So the input goes in, some multiplication, summations, some activation, and then goes to the next layer. Same thing happens, and so on till the last one, right? And the last one does all of those computations and give you a bunch of numbers, right? That is the output layer, right? Now, any layer in between, this is what we call it hidden layer, simply because this is somehow assumed to be hidden from the eyes of the input or output, right? So they actually compute a bunch of features, a bunch of numbers, which are useful for inference, for final result that you have, but they are not actually returned to anyone, right? They are just the intermediate computations, right? This is what we call it the hidden layer. Questions? No question? Okay, cool. So if you got no question, now can you tell me what is the depth here? If I want to go from the input to the output, what is the depth? 3. 1, 2, 3, right? Now, how many hidden layers I have? 2. I have also one output layer, right? So the depth is the number of hidden layers plus the number of output layers, which is 1 only, right? So it's going to be the number of hidden layers plus 1, always, right? So the depth of a layered neural network is always the number of hidden layers plus 1, right? Everybody's clear? Now, if I have a deep neural network, how many hidden layers I should have? At least 2, right? At least 2. So this is why people used to call it deep neural network. Because initially, when they started to just develop universal approximation theorem, they said, like, we can do anything with just one single hidden layer, right? And then they stuck to this idea for ages. But the problem was that the complexity was not possible to be handled. Because if you want to have just one hidden layer, you need to have it extremely large. But then they started to see that, oh, if we just, instead of one hidden layer, we make it 2 hidden layers, 3 hidden layers, and so on, then you can just shrink the size of every layer. And it's still as expressive as the other one. And because of that, they started to call anyone who has more than one hidden layer, they called it deep, right? So this is the reason they started to call it deep. Not that this is extremely deep. It's just deeper than what people initially thought of. So a deep neural network, so the depth is always the number of hidden layers plus 1. This 1 is simply the output layer. And because of that, a deep neural network has always more than one hidden layer, right? Questions? Everybody's cool? Yeah. Sorry? No, one output layer. This is one output layer, right?
Yeah, can I have more than one?
Well, it's not going to change your depth, but you could, yes. If I, for example, I get X, we're going to do it later, but if you get X and you process it up to very last layer, but at the last layer, you don't want to just compute one output. You want to just compute multiple outputs, right? Then you can just put output layers in parallel, right? So you could say X comes in, and then at the output, I am computing temperature. This is one of the output. I am computing, I don't know, pressure, and I am computing the volume, right? And then these guys go in, and then they come at different layers. You can, in that case, think that, yeah, either you have 3 layers in parallel, or you have one giant layer, right? But eventually, you don't have more than one layer, right? Because you can always, it doesn't change the depth, right? You can do crazy stuff, like you take some outputs and then again keep on processing, but then that is not going to fit the definition anymore. Questions? No question? Okay, cool. So that's it. Now, what about the XOR architecture that we had? The XOR architecture, the one which we designed to just learn XOR, this was actually a neural network, right? it was a bunch of perceptrons. They are all neurons with step function as the activation. So I can show it like this. And what is the number of hidden layers here? 1. So is it a deep neural network? No, it's not a deep neural network. This is what we usually call it, a shallow neural network. Just one hidden layer, right? Cool, right? OK, great. So now, eventually, based on what we started with, so the whole idea of machine learning, a deep neural network for us is simply a model, right? Why is this a model? Because eventually it's a parameterized model with, between input and output. So x goes in, y comes out. And it's parameterized, right? It has lots of weights in it, right? And if I change those weights, this connection between x and y is going to get changed, right? So this is simply a model, right? And, but it's a kind of giant model with lots of parameters, right? This is one thing. The other thing is that what are the hyperparameters here? What are the learnable parameters? Do you have any idea what is a hyperparameter? Anything that I need to specify to be able to draw my neural network, that is a hyperparameter, right? Number of layers that I have. Number of neurons within every layer that I have, right? The kind of activation that I'm going to use, right? These are all hyperparameters. If I want to just code, implement that neural network, I really need to know those parameters to be able to write the code, right? So this is what we call it hyperparameter, yes? You can think of it like this, but since it does not belong to the model, I wouldn't call it a model hyperparameter, right? Because you can have this one model and you can use different losses, right? So, but it's a kind of hyperparameter in your whole design. That's right. You can change it, yeah. So, but what are the learnable parameters? The weights and biases, exactly. So the weights and biases are the only thing that you want to learn, right? So you want to know how you should properly fit those, set those weights and biases, such that when the input goes in, what you want to see comes out, right? This is the only thing that you have. And universal approximation tells us you have plenty of choices, right? So you just need to find the right one. You definitely can find it. That guy definitely exists. The only question is that whether you can find it or not, right? Now, so as I said, anything that you need to draw your architecture, write down your architecture is the hyperparameter, and anything within the architecture is going to be the learnable parameter, and this is what you want to learn. For instance, look at this guy, right? This is the dummy example we had at the beginning. And here, the idea that I just put the input like this and then put the other neurons in between like that and connecting them in this form and specifying those function f1 to f4 here, these are all hyperparameters, right? I could have connected f4 to, I don't know, f1 and then get the output from f1, right? That was my choice. So if you want to write down the whole computation in this model, you need to first specify that, and this is the hyperparameter, right? But now, since we have the hyperparameter set, since we know the architecture here, we are now able to count the number of learnable parameters, right? So how many learnable parameters I have here? Yeah, let's do it together. So I have f1, for example. How many inputs does it have? 2. And there is one output coming out of it, right? Now, when it has 2 inputs, how many parameters does it have? 3. 2 weights, 1 bias, right? What about f3? Same. What about f2? Same, right? So all of them have 2 inputs. Each of them has 3 weights, right? 2 normal weights, 1 bias, right? So I could say neuron 1, 2, 3, they have each 3 parameters, right? 2 weights, 1 bias. What about f4? How many inputs does it have? 4. It's going to have a bias in general, so it's going to be 5 weights as well, right? So I have here 9 different parameters. Here I have 5. So in total, I'm going to have 14 different parameters, right? So I have 14 degrees of freedom that I can choose, right? I can put any weights for every neuron. I can put any bias. And by changing them, the relation between input and output is going to change, right? Everybody's cool, right? Questions? No question? Yeah.
The weights don't only impact the input at the beginning, they also impact subsequent.
Like, for example, here, say F4, this guy has also inputs from the other neurons, right? So the output of F2 is going to get multiplied to its own weight and then added to the other things, right? So the weights are essentially here on these edges, right? So anything that comes in before getting in, going to get multiplied with weights and then adds up.
Okay,
right?
they're not the same weights.
No, they are different. Like we have 14 different weights, so 14 degrees of freedom, right? Right. Questions? No question? Yeah.
So, my understanding is like you can choose multiple architectures for
Sure.
a certain neural network.
Exactly.
The weights are going to be different.
Exactly.
How do you sort of decide?
Yeah, this is what we're going to learn through the semester. But it's in general a hard question. But gradually, I mean, by experience, you start to have feeling about it. But you're right. I mean, if you have a certain number of neurons, you can decide to combine them differently. And each of them going to end up different number of weights and different capacity. This is totally right. Yeah. But at some point, you're going to see that these are, like, practically, these are easy things to decide. Yeah. Yeah.
So in this network, can we apply the function depth is equal to hidden layer plus 1 here?
Here, no, because this is eventually not, let me see. This is actually not a classic layered network, unless I think, because, yeah, I mean, you can't start designing layers like you say F3 is the first layer, and then F1 and F2 is the second layer, and F4 is the output layer, and there are a bunch of escape connections here, but I didn't mean about this, right? So I meant about that classic layered network. Yeah? Yeah. Questions? No question? Great. So if you got no question, now let's just, last thing, define the deep learning. What is deep learning? Is essentially machine learning, like the three main components, data, model, loss. When, as a model, you use a deep neural network. That's it, okay? So if you use a deep neural network to be your model and you try to address one learning task, then you're essentially doing deep learning, right? So deep learning is the subset of machine learning where you use deep neural networks in order to address a learning task, right? So one thing that you could, like you have model, loss, and data set, as I told you, and the model here, when you are doing deep learning, is going to always be the deep neural network, right? So we talked about machine learning, right? And when we talked about the machine learning at the very beginning, I didn't tell you that you are supposed to use any specific model, right? You can choose any model that you want. You can even design your own model, right? And then we talked about representation learning. I mean, just named it. And I told you in representation learning, you're thinking about designing a sort of model which is able to capture a good fraction of nonlinear representations, right? So that was the representation model, right? And now we have deep learning where we are using deep neural networks as the models, right? Now, obviously, deep neural networks are models, right? So deep learning should be a subset of machine learning, right? Because in machine learning, we talk about any model. Here, we talk about only deep neural networks, right? Now, deep neural networks, can they represent a nonlinear function? Yes, they can. So, yeah? So they can be a part of representation learning as well, right? So they are a class of models which are able to represent nonlinear models, right? There are also some other classes, for example, polynomial models, right? They are also able to present nonlinear functions, but they are not the classic deep neural networks, right? They are some specific models, right? So what you can say in general is that deep learning is a subset of representation learning, and representation learning is a subset of machine learning. Like machine learning is more general, and then in representation learning you say that, oh, I am dealing with very complicated functions, they are nonlinear, I need to have a sophisticated model. And in deep learning you would say, okay, deep neural networks are sophisticated enough that do all of it, right? So deep learning is a kind of representation learning, and all of them are a kind of machine learning, right? But that guy is so good that it's just dominating the whole literature, right? Because whatever you want to do, deep learning can do it, right? So it's a very good representation, and it's capturing pretty much any learning test that you want. So you have the big set, and you have the deep learning, but gradually through time, that guy got so big that somehow is covering all the machine learning nowadays, right? Not all of it, but a good portion of it, right? So this is just to give you a kind of understanding. When people say, like, oh, deep learning is a subset of machine learning, you understand what they are talking about, okay? Questions? Yes, you're right. Shallow neural network is a part of representation learning, yes. Questions? No question? OK, so yeah, that's pretty much this. So if I give you now a learning task, you are essentially able to use deep learning to solve it. So you can just set your data set, then you're going to set your model. It should be a deep neural network. You're going to choose one deep neural network, and then you're going to set the loss, and then that's it, right? You're going to go ahead, compute the empirical risk, and then you try to minimize it, right? So that's pretty much what we do all the time. But the main question that I have not yet addressed for you is that how we can minimize the empirical loss or empirical risk. So in that respect, we need to have an algorithmic approach. I mean, you cannot only rely on intuition, or, for example, you develop the algorithm for every single new architecture, right? So we need to have a machinery for that, and this is what we're going to do. There are a bunch of other things that we're going to speak about, like, for example, how we're going to use hyperparameter, what kind of architecture we can make, and this is basically what we're going to do in the next chapter. So we start with the basic feed-forward MLP, and then we're going to get into convolution, which is a better idea when we have a spatial correlation in the data, and we're going to get into sequence models as well when we have temporal correlation inside the data, okay? So the last thing that I need to just tell you as a preliminary is this idea of how we can design an algorithm which minimizes a function. And that function for us is going to always be the empirical risk, okay? But we need to have an algorithm, and we're going to see that there is a very simple algorithm known as gradient descent. And this is actually the base of any optimization algorithm that you have in practice,